let's talk about there are four molecular gauge here. Which one's being more acidic? Which one's being least less acidic? Let's rank these molecular based on acidity. Again, whenever you get this question, what you need to think about is what is the most acidic hydrogen in the molecule? And obviously, this one, hydrogen and carbons are typically not the most acidic hydrogen because if we talk about the carbon being least electronegative, I mean, among those major atoms, carbons are not most electronegative atoms. So hydrogen and carbons are typically makes it very less acidic. Hydrogens on oxygen, nitrogens are better candidate for the acidity. This one, definitely oxygen is having hydrogen there. That will be the one that goes out. And then you get the conjugate base with this oxygen being negatively charged. I mean, suddenly you get the sulfur here, but the same analogy, hydrogen and sulfur will go out because that's the most acidic hydrogen there. I mean, other than that, it's all on carbon. So this is a better choice. And then when this proton goes out, you get the sulfur having a negative charges there. And then same thing go for the next one, nitrogen having a hydrogen there. That's the most acidic hydrogen in that molecule. When the proton goes away, you get the nitrogen being negatively charged. I mean, unfortunately, this molecule has been oxygen there, but this oxygen doesn't have a hydrogen. So there's no proton to lose on that side. This has to be hydrogen on carbon that has to go away. So if this proton goes away, even though this is not something very acidic, but that's the most acidic one in that molecule. Right? That proton goes away, we get the carbon being charged. So these conjugate bases are something that we need to think about for the stability. The same thing goes, well, does it make resonance structures? And you can see that all of them actually make resonance structures, right? This electron density comes in, they get carbon oxygen double bonds like this. That pushes this type of one electron to double bond for oxygen. You get oxygen negatively charged. Same thing can be done with this one, and then all of them actually can make a resonance structure. So having a resonance structures doesn't really make any difference for any of these molecules. But now we can see that, okay, in this resonance form, it's all oxygen having a negatively charged, so that forms probably doesn't break the ties. So we need to think about stability in these forms of resonance structures. Oxygen negatively charged, sulfur negatively charged, nitrogen negatively charged, carbon negatively charged. So should we use electronegativity for all of them? Or should we use a size for all of them? If you're trying to come up with just one rule that applies for everything, then you are bound to make a mistake. So you got to think about a little different way. I'll do this way. Oxygen, nitrogen, carbon, those are elements of the second one. So when I'm comparing the acidity of these three, I would use electronegativity. Sulfur is bigger than oxygen. Right underneath of the oxygen, there's a sulfur. So if I'm comparing those two, I would use a size. And then what's being a reference molecule in these two comparison? At least we need to get a one same so we can put them in order. At least that ones can be worked as a reference molecule for these two comparisons that I'm making. And then we're going to put it together. I would say that might be a straight. So let's talk about these two first. Oxygen negatively charged, sulfur negatively charged. This is topic we already talked about. Oxygen is more electronegative than sulfur, but sulfur is bigger than oxygen. So which can handle negative charges better? The sulfur, because it's a bigger atom. So if you're comparing among those two, it will be that one being more stable than this one. So this is more stable than that one. At least we know that one. But I cannot directly compare this to that because these to that is a little different, right? They're having a different activity. I mean, size is still sulfur bigger, but it may not be straightforward. So I would say, after we do that, let's compare this one with that one. If you compare this one with this one, which ones are more stable? Oxygen is being more stable, or nitrogen negative charge is more stable. then you gotta use electronegativity because they're on the same side. They're the same second row. So this is the more stable than that one because oxygen is being more electronegative atom. It can handle extra electromagnetic nitrogens. And then obviously the carbon being negatively charged is worse than the nitrogen being negatively charged. So if you can rank them, at least this one is worse than that, and then that one is worse than this, and this one is better than that. So if you put all together, then we now have a ranking. This molecule is the most stable one. That's why that's the most acidic one. And that's the second one, that's the third, and that's the fourth. So sometimes you gotta compare things differently, even though we do the same question. So those are something that you gotta do. But if you do that, and then I'm pretty sure that you will come up with a good ranking that you need to come up with. But that's an answer. So that's the reason why you gotta develop practice. Sometimes a question can be sized for most of them, maybe 1% of negativity, it's a rational question, and who knows. I cannot tell what I'm gonna ask, but these are all combination of these factors. All right, let's talk about, there are 5 molecules here. Then we're going to talk about the stability and the acidity of the 5 molecules. And then you probably already know what to do when you see a molecule like that. You got to come up with the conjugate basis first, which is a P protonate forms, and which means that you got to find out the most acidic hydrogen for each molecule. And obviously, this is the most acidic hydrogen because that goes out. You're going to get the carboxylate. That hydrogen being most acidic one, you get the sulfonate here. That proton goes out, you got the oxygen anion right there. And then this one is a carboxylate again here. That's also the carboxylate. So we got 3 carboxylate, which is exactly the same. But we got the 1 sulfonate, 1 with oxygen anion. So it's not really simple. I mean, I would say simple, but you got to think about something else too. Well, this one, sulfonate, having a 3 oxygen being on the sulfur, meaning that you got to have 3 resonance structures. The more the electron density is spread around, it makes it more stable. That's the reason why the sulfonic acid is going to be the most strong one. I don't even need to do other things to find out which ones are most strong because it has the most number of resonance structures. So that's a strong one. I mean, you may think that, this is not as acidic as a sulfuric acid, but you may think the sulfuric acid is definitely more strong than vinegar, right? So that's something to know. What is the least acidic one? That would be this one. Because of that, 100% negative charges need to stay on single oxygen. It won't make any resonance structures. So this is the least stable one. So we got the number 1 here, we got number 5 there. But what about those 3? And they're all carboxylic acid. They're all going to make the resonance structure just 1. Then how can we figure out which one's going to be more acidic than the other? That you need to think about what other things in the molecule. For this one, you get the chlorine bonded, no chlorine there. You got the chlorine here, but that's a little further away from this carboxylate. The chlorine is not the most electronegative atom, but it's a decent electronegativity. It is good. So you can handle negative charges better. That's why the sodium chloride is an ion. It's all right. It is all well. We all know that chloride is not a bad ion. So chlorine will pull the electron density from this oxygen through the bond, and then what we call that phenomenon, inductive effect, right? So chlorine is going to be pulled electron density from the oxygen, negatively charged there. This one doesn't have this electronegative atom. So if I compare between these two, I would say this one's a more stable anion compared to that one, right? That I can say. But this one also have a chlorine there. There's a chlorine, there's a chlorine. The difference is, this one that's closer to the oxygen anion, that was further away. In order to make an inductive effect, electron density being pulled or pushed through the bond. If it's far away, impact goes down dramatically. The closer the better. Stronger the better, and then closer the better. So you got the chlorine closer to the oxygen ion with this molecule compared to the other one. Chlorine is a little bit far away, 1 bond away. So that means it's going to make the impact smaller, even though it potentially can withdraw the electron density through the bond from this oxygen ion, but the power is going to be less compared to this one because of this being closer. So if I compare this one with that one, I would say this one is worse than that one. That's more stable forms. So these all put it together, then you can say that this being the most acidic one by having a most number of resonance structures. Second one is this one. And the third one is that one. Even though chlorine is being far away, having it better than not having it. So that's number 3, and that's number 4. And this one cannot make a resonance structures. So oxygen has to handle this negative charge 100% by itself. So this would be the least stable one. So that becomes number 5.
And let's say that chlorine you're comparing to coal, is there a fact that closer makes it more better, or you just can't compare?
So your question is, if this change, we change this to the chlorine?
No, if you kept that, or
Yeah,
change
that change the chlorine? Yeah, you make it possible to report. Even I can solve that. So there are certain things we can answer, certain things I cannot even ask, because if I want to answer that question, I probably have to do the experiment and find out. I mean, the question you're going to get will be the reason. I mean, this organic chemistry is not like the God-given Bible, it only happened this way. No, we're just trying to figure things out by looking at this example, that example, by empirically, we kind of reason it out, right? If it's a too complicated cases, and then I just cannot, answer that question. So you won't have to worry about that. Okay? Hope that answers the question. I know there are so many different difficult questions we can come up with. Imagine that answer to those complex questions. Yes.
The number 1 or 2, how do we know that one is more stable?
This one being more stable, the reason is this oxygen, this molecule make a 2 resonance structures. This one, that one can make a resonance structure. I didn't draw here, it looks like this. This lone pair comes in, you make a double bond, this electron pair comes out, you make an oxygen ion. It makes a 1 resonance structure. Number of the resonance structure matter because that's how many atoms can share the state, right? The less it gets, each one gets is lower pressure. The more it spreads around, this always helps on molecular stability. So that's why this being most acidic, most stable, because of 3 resonance structures. This has a 2 resonance structure like this, even though the chlorine is not there. So that's the reason.